Hello everybody and welcome back. We're going to continue our look at the 2008 Friar. In the last video we dealt with question number 2, so we're over the halfway point. We're on to question number 3. Alright, so 3 has 3 parts. A. Figure 1 shows a net that can be folded to create a rectangular box. Determine the volume and surface area of the box. Okay. So we have a little net. We have a length 7 here, so that's 7, that's 7, that's 7, that's 7. We have some 4s, so it's going to have square sides and then a rectangular build for the most part. So, let's just redraw a picture of the net here on our scrap paper. Straight lines are always my bane with this program, but that's probably because I have problems freehand drawing a straight line in real life. I think that's looking pretty good. That's not bad. That might be one of the best nets I've ever drawn with this program. We get a 4, we get a 4, and we get a 7. So, this folds into a 4 by 4 with length 7. Not fodding, we want the word folding. So we get dimensions 4, 4, 7. So volume, I don't know why I can't spell today. Four times 4 times 7, so that's 16 times 7, and I think that's 112. Yep, it is. So we get a volume of 112. We were also asked for the surface area. So from the net, we have 2 4 by 4 squares. And that area is 16. And we have 4 by 7 squares. So that's going to be a 4, that's a 4, that's a 4. 4, 4, 7, 7, 7, 7, 7. And we have 4s and 4s here. So 4 by 7, that gives us an area of 26. So the surface area is 2 times 16 plus 4 times 28, so that's 32, plus 4 times 28, so that's going to be 144. So we got 112 for the volume and 144 for the surface area. And that's all we were asked for in part A. Alright, B part of question 3 on the 2008 paper. In figure 2, which we have below, the rectangular box has dimensions 2 by 2 by 6. From point A, an ant walked to point B, crossing all 4 of the side faces. The shortest path along which the ant could walk may be found by unfolding the box as in figure 3 and drawing a straight line from A to B. Determine the length of AB. Okay. So, we're unfolding this net. We can figure out the dimensions. Let's get ourselves a brand new piece of paper. Let's treat ourselves. Okay. So A is here, and we have 2, we have 2. We have B down here, and we have a height of 6. I think our net looked like this. We had A, and we have B. Yeah. Okay, so we've drawn our net properly. You need to use that point C in a moment. So from the dimensions in figure 2, we can input lengths on our net. So we get 2, we get a 6 here, we get a 2 here, and a 2 here, and a 2 here. So with point C as shown, we see AC is 6 and CB is 8. So 4 copies of 2 added up together. And because we have rectangular faces, we know that this angle in here is right angled. So by Pythagoras' theorem, we have AB squared is AC squared plus CB squared. And that's going to be 6 squared plus 8 squared. And you might be accustomed to this one, a 6, 8. We're going to have a length of 10 over here. But we need to actually show that we know what we're talking about, because this isn't a final answer question. So the ant travels a distance of 10. Put a little box around it, nice and neat. So we determine the length of AB. We know how far the ant has traveled. All right, C part, the last part of question number 3. In figure 4, which we have over here, the rectangular block has dimensions 3 by 4 by 5. I smell a 3, 4, 5 triangle coming up. A caterpillar is at corner A. Determine with justification the shortest possible distance from A to G along the surface of the block. Okay. So just as in the last question, where we unfolded the net and tried to find the shortest distance being a straight line between A and B, to get the shortest distance between A and G, we're going to have to unfold this box into a net. The problem is there's going to be a couple different ways we can unfold this net. So the caterpillar could go along the front face first and then go along the right face to G, or it could go along the top and then along the right face to G, or it could go along the top and then along the back to G. There's lots of different ways to unfold this net, giving us different possible answers. So let's explain why we're unfolding the net. That way we get full marks. Right? We've justified what we're going to do by likening it to what we did in Part B, and what they suggested in Part B of finding the shortest distance. Okay? You wouldn't need to go ahead and prove that using this net strategy gives us the correct answer. I mean, it's the grade 9 contest. And that's, I mean, at best, a first-year university-style explanation, proving something like that. And we don't do a whole lot of geometry anymore in math education. So just justifying it by saying shortest distance between 2 points is a straight line, and we unfold the net to find such a line, that's easily all you need to do to justify this. The real heart of the question comes in determining which of the possible nets to use. All right, so what were the dimensions and where? So 3 back, 5 on the bottom, and 4. All right, let's redraw our picture. So A is here, G is here. I think it was A, B, C, D on the top. E, F, well, maybe I'm wrong. E, F, G, H, okay. Oh, sorry, that's 3, not 5. We have 4 top and 4 on the side and 5 on the bottom. Okay. So what could we do? We could unfold it with we're gonna have A here, B is here, C is here, D is here, C, H, G, E. Then I guess we could stick another one of these under here. That's F. That's B. That's A. That's E. E, F, G, H. Okay, so we can either have 4 and then a 5 and then a 3. It's giving us a right angle triangle of 4, 5, and 3. Or what's another one we could have? We could have A, D here, and then C, B, H, G. So we'd have that. H, and that would be E, F. You don't have to fully label it, I'm just choosing to. A, D, E, F, G. So that would be a 5, 3, and a 4. Okay, so that's an 8 by 4. Oh no, we already have the 8 by 4 triangle. Oh, 5, 4, and a 3. And then we have one more. And that gives us A, B, C, D. Put G here. F. I don't really care about the rest of them, but it's an H here and an E here. And A here. D. It's really hard to unfold nets. BF, I think that's A, E. So HD, that's going to be G and C, I think. But the point is we get another right angle triangle. And it's going to be a 5 by 3 and then a 4. Admittedly, there are several other nets, but these three give us the so that gives us 3 different right triangles. So we get we had 5 plus 3 plus 4. We had 4 and 3 plus 5, or 3, 4 plus 5. So to find the shortest distance AG, we need the shortest hypotenuse. Alright, well, so we could have 5 squared plus 7 squared, we could have 4 squared plus 8 squared, and we could have 3 squared plus 9 squared. And I think this middle one's going to do it. Let's rewrite this. Let's write this a little better so it's a little more clear, because clarity does count on these contests. You could have AG equal to square root of 5 squared plus 7 squared, or 4 squared plus 8 squared, or 3 squared plus 9 squared. So square root of 25 plus 49, so square root of 74, or 16 plus 64, square root of 80, or 9 plus 81, square root of 90. That's shortest. So, and let's just double check we weren't asked for anything else. What is the shortest possible distance from A to G? And determine with justification. We certainly did. Shortest possible distance from A to G. So square root of 74. 74, does that have... no, it's just, it doesn't have any squares, so square root of 74. That's the final answer. If it had a factor of 4, we could take it out and say it was 2 root something, but 74 is just multiples of 2 times 2. It's 2 times 37, so there's no perfect square to take out of there. So that concludes question number 3, part C, and that finishes question 3 off completely. It's a nice little three-dimensional thinking problem that really reduces just down to a two-dimensional problem. And this, caterpillar crawling along this distance, ant walking along this distance, these questions pop up from time to time, and it's all about unfolding your three-dimensional structure into a two-dimensional net and figuring out the shortest distance from this point. The first time I ever saw a question like this, I think, was way back when it was a Fermat or a Cayley or something like that, and there was an ant traveling from the outside of the cylinder to the inside of the cylinder, and you had to show that he sort of makes a straight line, a beeline for the top of the cylinder, because he's got to go from the outside over the top into the middle inside of the cylinder. But all these questions are basically the same. They pop up from time to time. Take your 3D object, unfold it into a two-dimensional net, draw a straight line, and you're home free at that point. So that was question number 3. Hopefully you liked it, and you will join me for question number 4 in the very next video. So I'll see you guys then.